Okay, cool. Okay, so yeah, I think we can start, and people can can join afterwards. Not an issue. So, well, first of all, thank you, Carla, for coming here to present. I know you are here with Nikitas and also Anca Nitulescu, who is in the chat. So thank you all for coming. Today you're going to speak about FLIP-and-Prove, in one of your latest papers, where, if I understand correctly, you propose a new folding scheme and also a way to prove relax R1CS on a much more, let's say, optimal way. Thank you very much for you all to attending, and the floor is yours. So feel free to start.
Thank you very much, Carlos. I will present this work, and I will have distinguished two parts. Like, first, I will start with an overview where you will see like these beautiful slides. They are when you see beautiful slides, they are from Anca, which I like messed around. So if there's something that is no longer aesthetic about the slides, is because I modified the beautiful slides from Anca. And then, since I understand that you want to hear also like a bit more in depth, for the more technical part, I will use like some other slides, like say more mathy slides. Okay, so let's start with the overview. So what is our motivation? And when we started, like, we had a concrete application in mind, which was the Filecoin proofs of storage. And there we have like storage providers, and they are really regularly proving storage. And they have to, so they keep like regularly making SNARK proofs that they are really are keeping sufficient space for the data they have to store. And as you probably know, like in this application, it's like, as far as I know, currently one of the largest instances, like where we're like regularly proving like many R1CS, doing many R1CS proofs. Okay, so the situation was something like that. So for each unit of space, there was like something like 10 SNARKs, and these were like submitted on chain. This was the original solution, which of course, like, you know, that this require lots of space, right? For this, to minimize the costs of like storing these large proofs, also maybe the cost of verifying them, the cost of proving, there was like a previous solution. So yes, sorry. And all these NARCs, they are for R1CS proof system. So like maybe the general idea is that our results are also for other types of constraint system. But in this particular case, this providing these proofs required doing lots of R1CS proofs. As you know, R1CS, which are rank constraint systems, it's like a characterization of NP, and it's commonly used as an abstraction to describe the kind of constraints, the kind of thing you need to prove to do as SNARKs. So the topic of this talk, motivated by this application, but I think it's like a general case, right, where you want to prove many R1CS instances, is to study how to prove many of multiple R1CS instances in different ways. So how can you save on different parameters? Of course, like the first solution that you can do is like just to prove naively, right? Like you have many statements, many R1CS statements, and you just prove individually each of them. What else can you do? Well, there's another like classical thing to do, which is like save on verification. You just compute individual proofs, but you just can do some probabilistic techniques to do a random linear combination of the proofs or something, so that you are saving on verification. But you're, of course, not saving on either storage or prover time. Other approaches is to have aggregation, okay? So what is the difference on aggregation? So here we're not saving on prover time because we're still computing the individual proofs, but we're saving on storage because we find a way to store all these proofs in a compact way. Finally, another way of achieving this is to recurse. Okay, so like the idea is, as you very well know, the idea is like you keep sequentially like making proofs, and in each step you prove that you have a that the new statement is true, and also that you have a proof that the previous statement is true. As you know, this has like many advantages, and as you know, this is like why is this so popular? And like the advantages are that you save a lot on prover memory. The verifier essentially has the cost of like verifying one instance, and like the proof doesn't grow, right? Of course, you also know that this recursion comes with a lot of engineering challenges, including, for instance, the need to use cycles of elliptic curves to make proofs that are correct. So you need to somehow arithmetize the circuit of the verifier. And to avoid doing non-native arithmetic, you need to move to some cycle of elliptic curves or something like this. So this solution, although it's like fantastic and it's very interesting, it comes with lots of engineering challenges. And also there's like some kind of prover overhead because you're arithmetizing the verifier circuit, right? So like in the next step, like in the second proof, you need to prove not only the original R1CS instance, but you also need to prove that the verifier would accept the previous proof. So then in this setting of recursion, as you probably also know very well, there was this idea of folding statements, which is the idea of, so what is a folding protocol? Like it's an interactive protocol between a prover and a verifier where they reduce two different statements with their witnesses to a single statement. Okay, so the verifier is like a public coin verifier who's like changing and sending just some challenge. The prover is sending some cross terms, and at the end, together they manage to reduce this to a single instance. This has been used like in the context of folding, and the idea is that the same idea of recursion, but like now each of the steps is very cheap, right? Because instead of doing a proof that the previous step would be, so doing the full proof, so proving with a SNARK that there was a satisfying instance, what you do is you just keep a running instance of all the commitments, and you show at the end that they satisfy some relation. This has like the same, this is much better from the point of view of the prover, as you know, because first, for two reasons. First, because each of these steps is essentially much cheaper than computing a full SNARK proofs, and also because the verifier of the folding relation is also usually much smaller than the verifier of a full SNARK. But we are in the same situation, right? Like this is still difficult to realize, apart from other issues like maybe privacy, right? Depending on who verifies this. So in the case there's more than one prover, although this is also the setting that we will consider in this talk. So when we have something like recursion via folding, usually we think of folding as like this step of reducing these multiple instances to a single one. And usually then we have at the end to a single instance of something called relax R1CS that I will tell you more about later, although I'm sure also that you know. And what we have here when we're using recursion with folding is that usually this last step, as it's currently implemented, there are like two solutions to prove this one step, like one or three. So one solution is like you do nothing at all, right? Like you don't create a proof because like maybe your fault statement is so small, it doesn't pay off. But if you want to prove it, you maybe use, as in the NOVA paper, you can use Spartan, or if not, you can also use Growth 16, but then you have to adapt Growth 16 for proving this. So you have to create a circuit that proves that this relaxed R1CS instant is at, so that you have a witness for this thing. So it's not really native, like you're doing some arithmetization here. So another option that you can use is like using option with folding without cycles, right? At the end, what is folding? Well, it's just a way of reducing two statements to a single one, right? So like you don't really need to prove that the folding was correct, but you could also just keep reducing like many statements to less and less and less. Okay, so you can start with two statements, reduce it to one, then get another statement, reduce it to a single statement, and so on. And you don't need to prove that you've done this correctly. You just can let the verifier check that. Okay, what's the problem with this approach? Is that the verification is linear in the number of statements, right? Somebody has to verify that you're doing all these folding steps correctly. I'm emphasizing this because although folding was proposed in the context of recursion, and maybe this is how it's most often used, in reality, this is, you can just do folding in any curve and without any need of cycles, and you can just think of it as a way to reduce several statements to a single one. Then when we follow this approach, we're still in the same situation, right? Like we are folding we are doing several steps of folding, and we end up with a single one relaxed R1CS statement, okay? And again, we have the same issues here, so we have to think how to prove it. So this is the same as in the recursion setting, okay? You have to think how you want to prove this last step. But what's different, let me emphasize, what's different from using folding with recursion or without recursion is that here, if you're not using any cycle of curves, you still need to read and check that all the statements have been folded correctly. What do we propose? We propose something that we call FLIP-and-Prove, which can be summarized as simple communication efficient folding. What's the idea? Why do I say it's simple? Because it avoids some of the complexity because it doesn't go through cycles of elliptic curves, and but it doesn't incur into this problem that if you don't use cycles, you need to verify all the steps. Compared to previous approaches like aggregation, you still have the benefits of folding. So you are not doing any Fourier transform in all these parts. And the second part of our contribution is this a protocol for this last step, a specific, a sort of like Growth 16 to prove this step, but where you're not like trying to write, so you're not really modifying the circuit that you're proving. So like essentially, it's a Growth 16 that allows you to prove this step, but for the same circuit as the original R1CS instance. Okay, so in summary, the advantages of what we propose is compared to batch verification. In batch verification, we had large proof size, but we are reducing the prover time, but also large proof time. In aggregation, we are increasing the proof time because apart from doing the individual proofs, we are computing the proof aggregated. And we also have like reduced verification and reduce storage proofs. And what we propose is to keep this like low communication cost. So it's like in aggregation, we somehow make all the proofs compact. We also keep this short verifier time compared to, so equal like in aggregation, but we massively reduce the proving time because of following this folding approach, right? Where we are essentially reducing many instances to one, and then the expensive step, which is folding, which is proving with a SNARK, we only do it once. Note also the difference with recursion, okay? In recursion, you have like some overhead for the prover because of verifying so arithmetizing the verifier circuit. But of course, like you have like other very good advantages, okay? So the main advantage with respect to recursion is the complexity. So it's like a really simpler solution. Okay, so let me review very quickly. So for this particular application we had in mind, which is proving multiple R1CS instances, and in particular, this Filecoin application, there was like a solution that was designed for this setting, which was SNARK-Pack, okay? And this is a paper of Nicolas Gailly, Mary Mahler, and Anca Nitulescu, where what they achieved is getting like many different SNARK proofs, like Rook 16 proofs, and from this they created a single aggregated proof of size logarithmic in the number of statements. Like what I want to emphasize about this solution is the techniques that they used. So how did they achieve this shorter proof size? How do they achieve this reduced communication complexity? Well, they used something called two-tier commitments. And the starting point is the observation that if you want to verify many SNARKs, so if you have many Growth 16 proofs, and Growth 16 essentially is like the proof consists of 3 elements, and you have like many of those. What you need to make sure is that these group elements satisfy like different pairing-based equations. How can you do this compactly? Where there is this technique called proofs for inner pairing products, which is a paper of Bunz, Mahler, Mishra, Tyagi, and Vesely, where they suggest what they do is like they sort of build like a bulletproof proof system. So, so it has all the features of bulletproof. So like logarithmic communication, logarithmic number of rounds, where the idea is that you're committing to these group elements, okay? So you have to prove that many of these type of equations are satisfied, and somehow you manage to communicate all the terms that are all these group elements succinctly. And this is achieved by a tool called algebraic commitments to group elements. Okay, so so you have many. So how does it work? You have like many SNARK proofs. So this means you have many terms A, many terms B, and many terms C, and you create a commitment to those with these algebraic commitments so that you get something that is succinct. And then in logarithmic number of rounds, you manage to prove that these things that are inside the commitments are satisfying all the Growth 16 verification equations. So you never really send the proofs, but you just prove that these proofs exist and that they verify. What I want to emphasize here, because we will also be using similar techniques, is that in this context, we are thinking of these proofs for inner pairing products as a tool to prove the satisfiability of many pairing equations. Okay, so we have these pairing equations, which are the verification equations, and we are proving in a succinct way that we know a solution of all these equations. Okay, so with this basic solution that already exists, we now move to present our solution. For this, very quickly, because I think most of you already know that, we talked about how to do folding for R1CS instances, and this is something that comes from Nova, a very well-known paper by Kotapalli, Sethi, and Ciala. And the idea is that we have an R1CS instance. And we are trying to fold it. So what we're trying to do is from this R1CS instance to, in a probabilistic way, from this one and another one, reduce it to a single instance. So we start from, this is our starting point. We have two different instances, and what the NOVA introduces is a new relation, which is relax R1CS, okay? That it's relax R1CS because if you can see that it's a R1CS is a special case of relax R1CS, right? If you take that the error vector is 0 and this normalizing factor U is 1, then you get exactly an instance of R1CS. So why is this useful? Well, the idea is that if you fold to R1CS instance, you get a relaxed R1CS instance. And then you can continue the process, right? And then if you get two different R1CS instances, you get a new R1CS instance. So this is R1CS, let's say it's not foldable, but we relax R1CS is amenable to folding. Wait, okay, sorry, okay. So we will see this in more detail in a second. Okay, so this was the basic motivation, okay, the basic concept. So also to how to do relax R1CS. And now I move to do a more technical deep dive. So we have the ingredients. We have talked about folding R1CS, and we have talked about these commitments to commitments. Now I will tell you a bit more in detail how these commitments to commitments work. So our point of comparison is the Pedersen vector commitment, okay, that you all know. So we are in a group of prime order, and we have like a key that is just a group of a vector of group elements. I don't specify the distribution. You can define this key in different ways. Okay, so let's say it's just some distribution, and then, as you know, when you want to commit to a vector in integers modulo P, what you're doing is essentially an inner product, but in the exponent. Okay, so you're doing a random linear combinations with this key and these coefficients that are the vectors. Why is this binding? Well, the idea is like if you manage to find two different openings, then you are able to find a vector of scalars such that the inner product with the commitment key is 0. This is actually this is actually a hard problem for many G's. So as for any reasonable G you can think about, this is a hard problem, which is actually equivalent to the discrete logarithm problem. It's sometimes called the find rep problem or discrete log relations problem. Okay, so examples of distribution for which this is hard, it would be like, for instance, a uniform distribution, or also powers of tau. Like you can also take a structured commitment key. Okay, everybody knows this. Like, why am I telling you about this? Because you can make a parallel and to see how you commit to group elements, okay? What's different in the case you want to commit to group elements? So what you have here is that you have a group key, okay? So you're now not in just a group, but you also have like a bilinear pairing. I'm using additive notation for all groups. Maybe that's not very useful and not very usual, but I think that is better for illustrating the linear algebra that you're using. So the difference now is that your commitment key is actually a vector of group elements, but in the second source group, okay? So, and to commit, you're committing to vectors of group elements in the first source group. Okay, so what you have is, here's the commitment key, which is in this group, and here's the vector. And again, the commitment is just an inner product, except now this inner product, what it means is that you're doing like this linear operation, which is like this bilinear operation, which is the pairing instead of exponentiation. So you're doing the inner product of the message with a group element. So your final commitment is just a target group element. How do we argue about binding here? So if we managed to find two different openings. So again, this means we managed to find like some vector of group elements in source group 1 such that their inner product with the commitment key is 0. Again, this is the hard problem, right? So you have to find a vector of group elements in source group in the first source group such that the inner product with G is 0. Okay, it should be a 0. Is this a hard problem for different G's? Let's see. Let's try to find examples of this when this is a hard problem. For this, let me see a small example of a commitment to group elements when the length of the messages that I'm committing is just 2. Okay, so in this case, imagine I just pick as a commitment key the powers of tau. So I have P2, which is a generator of group 2, and I have tau times P2. How do I commit? Well, I just do this linear combination. Is this binding? Unfortunately, this is not binding if the adversary also receives the key G in group 1. So if it receives also these powers of tau in the other source group, we don't have a binding commitment, okay? Why is this? Well, look at this at this message. So if I take this message M prime and I just define it like that, okay? If I commit to this one, well, you can observe that the result is 0. So essentially, I'm able to construct a commitment for which the commitment is 0. Okay, so in particular, this means that I can find for any message that I want more than one way to open it, okay? Because the commitment to this message M can also be open to the message M plus M prime. This is more general than that. Also, if I choose like it's not only this message M prime, so I can randomize this fact, right? So if I choose this message, which is like a randomization of the previous one, this is also a commitment to 0. So in particular, I can find many different ways of opening a commitment. This is something that was also a problem, and for instance, in SNARK pack. And the solutions they suggested was just to move to using double, so like using 2 different commitment keys. Okay, so now the idea is like you get 2 different commitment keys with same structure, or actually it could be I'm not using anything in particular about, in this example, you could also talk about uniform distribution, okay? In general, it's an example, it's a problem if you have the key that you're committing, like you have it in both groups, okay? So the solution out of the box, let's say, is to get to do double commitment. So you commit the same to the same message with respect to do different keys, okay? So this is the commitment to the message with respect to C1 and C2. What's the problem about this? Well, obviously the problem is much higher communication costs, okay? This is a hard problem, so it's sound, but you get very high communication costs. The efficient solution that we use, which avoids this problem, is a solution proposed by A. Plonk, a paper called A. Plonk, by Ambrona et al. In 2022. And the idea is to avoid this growth of the commitment, so the double increase on communication length. The idea is to think of this not only as commitment to group elements, but also as commitments to commitments, okay? So here we're really using the fact that these are 2 tiers commitments. So we are not just using this scheme to commit to random group elements, but we are really using this scheme to commit to commitments, okay? So the situation that we have is we have a bilinear group of prime order, and we are committing to these group elements. And we have the adversary receives this key in both groups, okay? Okay, so then the solution is just to commit normally to it, but in the soundness analysis, what we show is that if you can open this commitment to another commitment key, so if you can open M1 with respect to another commitment key, CK, and M2 with respect to another commitment key, CK, that is independent of this key that you're using for committing to the target group, then this is still a hard problem, okay? So it's hard to find a vector of elements in G1 such that they break binding, so that the inner product with the commitment key G is 0, and at the same time open each of these vectors in the first group with respect to another commitment key, okay? So what's the intuition? The intuition is that this is the only way to break soundness, okay? The only way to break soundness is somehow use that you have the key in the other group. So the only way to break soundness is to put things here that are related to the commitment key capital CK, okay? So if you are committing to things that you know for sure they don't open to anything related to capital CK, then your scheme is still valid. Okay, so this is like an important technique that I hope gets more attention from this paper, A-Plong, that I think is quite useful, and I wanted to show you this technique, okay? So, and what our contribution is to also give a different formalization or writing of this technique. Okay, so then remember our key idea is to use folding in combination with these two-tier commitments, okay? And as I already gave an overview of how does folding look like, and in particular, a bit more technically, the folding protocol looks like that, okay? We have a prover that has two different statements that are committed relax R1CS, so they are like relax R1CS, where you have a public statement, a scalar factor, a commitment to error terms, and a witness. And the verifier just knows these two statements, and the prover also knows a witness to them. The important thing here is like the verifier is sending these cross terms, and it gets then a challenge from the verifier. Okay, and the result is just that the prover gets a single witness and the verifier gets a single statement. The two things to notice is that the prover is sending these cross terms, and second, that the way we are building the new statement, okay, E and W, we are using like different linear combinations. So for the new error term, we are having the previous error term, the second error term, and then these cross terms in the middle. But the coefficient we're using for the error terms is chi-square, and which is different from the other part. Okay, nothing new here. Now we move to talk about our solution. So what's our solution? So first, observe that you can fold R1CS instances in parallel, okay? So imagine now that you have 4 different statements that you want to prove, and you can essentially run the same protocol for R1CS, in which you are folding W1 with W3 and W2 with W4, right? But you can do them both in parallel. So how? Well, you just have to send the cross terms, 1, 3, 2, 4, right? You're mixing 1 with 3, 2 with 4. And And then you do the linear combination for each of the terms, okay? At the end, what you get is that the verifier, the prover gets 2 different witnesses, the verifier gets 2 different statements. Okay, so in general, so this applies, of course, in general. Let's say you have different, so k different instances, and you can like fold them in parallel, right? I can fold W1 with WK half plus 1, WK half with WK. And this means this involves sending k half cross terms, okay? Each, I'm mixing this with this, so I need to send the cross terms with this. Okay, so now I use this idea for doing parallel efficient folding of R1CS. And the idea here is that instead of sending all this, the prover and the verifier now no longer have many different R1CS instances, but instead what they have is a commitment to many relaxed R1CS instances, okay? So the verifier does not know all the individual statements that, so it knows the individual statements, so it knows xi and ui, but it doesn't know the commitment to all the witnesses. And it doesn't know the it doesn't know the commitment, it doesn't know all the commitments to the witness. Instead, it knows a commitment to all the commitments to the witnesses. Okay, so you're sending all the commitments to W1, W2, to W3, to W4. Instead, you're sending a single target group commitment, and same thing for the error terms. And here you would need to send 2 error terms. Instead, the idea is also to send a commitment to all these cross terms in the target group. Okay, if we do that, well, the verifier can no longer obviously construct the new error terms with this, because it doesn't know all the error terms, it doesn't know all the witnesses. And the idea is to have something related. It like actually looks very close to bulletproofs. So the idea is now the witness is split in 2 with the left part and the right part. The commitment to the error terms is split in 2, the left part and the right part. And the prover is just sending these halves of the commitment, right? So that folding can be done in parallel. So you're folding like that. So the left terms, so the same linear combination you were doing before, now you're doing it in parallel with the commitments to the first half and the second half, right? So if you check that, like, what is this? So this is the commitment to E1 and E2, plus a challenge, which is a commitment to 1, 2, so 1, 3, and 2, 4, and this is a commitment to 3 and 4, okay? And you can check that what you're doing with this is getting a commitment. So what you're doing is actually you're folding W1 with W3 and W2 with W4, and you're just doing it in parallel in a succinct way. Okay, and so what do you get as a result of this process? So you get that the witness, the prover has these 2 witnesses, no? We have 4 instances, they get reduced to 2 witnesses, and the verifier has these, keeps a commitment, but it's a commitment to a vector of half the size, okay? So he has folded W1 with W3, W2 with W4. And same thing for the error terms. So what we're using here is the homomorphic commitments of these 2-tier commitments. So if you compare with NOVA, like if you were trying to flip without cycles, what you would be doing is something like that, right? Like you can also build a tree of things that you want to fold, but you still need to check every step, right? The verifier needs to know that these 2 commitments and check they are folded together in a new commitment, and same thing for error terms. what we are doing is like somehow like we are doing a single commitment for each step of the folding, okay? So that in each step, I'm folding this one with this one with this, and same thing for the error terms. So this is like I want to emphasize that this is like a novel use of in this inner pairing product equation, inner pairing products argument. At least that's how I see it, because usually, as I said, you think of this inner pairing product as a way to prove that many pairing products equations are satisfied. Instead, you're thinking of this inner pairing product argument as a way to fold many things in parallel with very in a very communication efficient way. Okay. So in reality, so a few more details. How does the protocol work? As I said, like you send essentially one commitment to the witness and one commitment to the error term per level, right? Like you're sort of like building a tree of statements that you're folding. In the base level, like at the leaf level, you have to check that you start folding R1CS instances, so you really have to check that this is well formed. So you will check that all the terms U are equal to 1 and the cross terms are 0. So this you check at the leaves. And then when you get to the root, what you get is a target group element. And what you do is like you open this target group element. So at the end, when you finish your folding, you have a group element so something in group 1 and something also, there are terms also in group 1. So that you really have like a new statement that is a committed relaxed R1CS. Like it has exactly the same shape as if you had been folding this thing on parallel. So there are a few things that I didn't really tell you. So there's like a few extra details that are related to the commitment keys, like that you probably know if you have worked with bulletproofs before. So so let's say a few things about these extra details. Like the first thing is that I think this is the important thing to understand and highlight about this protocol, is that what you get in the last step is like a commitment to a group element, which is actually a linear combination of all the previous commitments. So it looks like exactly like folding, except that the randomness you're using has really like tensor structure, okay, which corresponds to really like folding things in parallel. So it's some kind of de-randomization technique where you're like folding, but with fewer rounds. And all the error terms and everything is consistent with that, okay? So we're getting like the error terms with that correspond to folding like that. The other thing to note is that what we get in the last round when we are opening at the root, so because we end up with a target group element and we open it, so it means that we have to give some W and some W prime such that this is holds. So we have to open this with a certain specific commitment key in the second source group, okay? And this commitment key, as you know from bulletproofs, looks like that, okay? And as you know, this it's a problem because this means, in fact, that if CK1, CK2, CK3, and CK4 is the original commitment key, this requires a linear number of operations in the number of statements you want to aggregate. And same thing for the error terms, okay? If you are to compute this key, you would actually need to do a linear number of operations. Luckily, there's since we are in a pairing group, okay, we have not moved from the same pairing group from the beginning when we're aggregating all the statements. There's this technique from Doris where that tells us that if we are using this commitment key that are structured, we can achieve logarithmic communication. Okay, So this was the FLIP protocol. What I think is interesting about the FLIP protocol is that it's to open the door for folding other relations, also with this inner pairing product, so that is actually you get something that's communication efficient, and it probably cannot substitute recursion in many settings, but there are settings where probably it's sufficient and it's a much simpler solution. You can use pairing groups, nothing special about these pairing groups. You can use BLS 12381 or whatever you need. Finally,
Carla, can I ask you a
yes.
question?
Yes.
I just can answer it to myself. Can we have non-uniform folding with flip? Because if you are proving that you have commitments to commitments that open to correct places, this argument is just so generic that I don't see why you could have non-uniform folding working in flip. Like, is there anything that prevents this from happening, or in fact you can just fold anything that you want?
So actually, I think that's actually the thing that I want to look next. Like, I didn't really look at it but I'm quite sure that you can do so that you can, like, again, what you're using is the homomorphicity, right? And I don't see a reason why you cannot do it with other relations. I didn't explore this yet because of the time, but I think that it probably works, and I think that's actually that's the nice question to look for.
Okay. And one other question that I have is, when you say folding in parallel, can we assume that you can plug in the PCD compiler from Boons et al. Into your construction, or parallel here means, I mean, there's some level of parallelism, I see that, but usually when I assume that you can fold in parallel, it means you can just plug in the PCD compiler there and have tree-like folding, basically.
Yes, but like, we are in a very different setting from folding, right? Like in folding, like so here you still have to verify all the steps you're doing, like, and there's no way I don't know, like, there's no way I can prove that this was done correctly from another proof and so on. So like, I wouldn't know what.
That's fair. That's fair, I see.
Yeah.
Okay.
Okay.
Yeah, that answers it. Thank you very much.
Yeah. So it's really like, I think the setting of recursion is like out for this talk. So because it's like sort of the point, right? That we are going to something that is like not recursion, but maybe simpler for many occasions.
Sure, that makes complete sense. And I mean, if I can ask one more question, sorry,
Yes,
for being annoying.
No, I prefer to get asked.
So one of the tricks is that you are basically getting, you are halving the costs of the things that you are passing between prover and verifying. Let's say, like you showed it with the cross terms, for example. My question is, does the arity affect, do you get a blow up factor in the cross terms the more instances you want to fold in together? Like, instead of doing 1 with 3 and 2 with 4, if you have now 8 instances and you want to just eat that up at the same time, do you get a blow up as it happened in Nova or not?
Yes, you do, because it's like the technique is the same, right?
Okay.
Like, so for here, like, the cross terms are like that. So it's essentially the Nova, sorry. It's essentially the Nova cross term. So naively is this. Now, again, the question is, and that's the work that I think is interesting, is to get all these techniques, no? That, as you said, Nova had this blow up factor. Then some papers found solutions for that. Like, you can move these solutions to this setting, and then let's see what you get.
Sure. That makes sense. And the last one that I have is also about this halving of the communication cost. You are in fact halving the communication cost in these areas. I completely agree. But when you are passing the commitments forward, those commitments are much bigger, as we are in GT rather than in G1 of many of the curves that we will be in Nova. So how do you account for that? Is it still worth it?
So what I don't really get is why do you say it's halving the communication cost? Because it's actually making it logarithmic, right? Like you get something like that. This is the situation. So again, I'm doing Nova, but with that, like I'm comparing to Nova.
Okay, sure, yeah.
Okay.
I see what you mean.
So here you need to read all the statements and verify they are pulled correctly.
So it definitely makes it worth it then to send GT elements around. Like you just don't care about it. It's worth it, like for sure. Okay, that makes sense.
I think so.
That makes sense. Thank you very much.
Okay. So now we want to talk about the last step. So which is how do you prove growth 16 for relaxer? So how do you prove relaxer 1CS? And you want to do it in the most communication efficient way. Okay, so you can optimize when you're designing a SNARK, you can optimize for different parameters. And what I try to do here in this design is to get something that is as communication efficient as possible. Okay, so let's start. So I will just give the idea. So the idea is, let's start with growth 16. What's the overview? As you know, growth 16, like it's not so, you don't have to read everything, but you probably have seen growth 16 before. And it looks, the structure reference string looks something like that, right? Like you have many of these linear combinations that include alphas, betas, and so on. You also have these terms with involved T of x, which is the vanishing polynomial at some group of roots of unity. And why is growth 16 so special? Well, it's because it's has very, very short very short proof. It's just 3 group elements, 2 in group 1 and 1 in group 2. And to verify it, you just do 3 pairings. Okay, so the verification equation looks like that. So as you know, like one of the drawbacks of Prop 16 is that the setup is relation dependent. Really, so if you change the circuit, you really have to change completely the structure reference string, because actually, as soon as information about this delta is leaked, then you can prove like arbitrary things. So you really need to get like a new delta for every time you do a circuit. Okay, so if that's growth 16 is like relation dependent, like maybe it's strange that we can like sort of adapt it to prove relax R1CS, right? So why does this work? Why can we why can we modify it a little bit, growth 16, and still be able to prove relax R1CS instances? Well, because if you, the thoughts, so at least that's how I understand it, for growth 16, there are like 2 parts, okay? So essentially, growth 16 is a way to prove very compactly 2 different relations, ignoring the fact that you also have to prove things about the public input. So on the one hand, you're like adding these terms because you are proving like a Hadamard relation. So you're proving that there are some vectors A, B, and C such that the component-wise product is equal to another vectors. Oof, sorry, my cursor. Okay. So, and this is related to some quotient you have to compute for this Hadamard relation. On the other hand, you have these terms, which are thought to prove linear relations. And this is what, these terms are what make somehow growth 16 not universal, because this way of proving linear relations, so you're trying to prove that this vector ABC that satisfies that Hadamard relation, they all have implicitly here the same vector Z, okay? This is the building blocks of growth 16, the main ideas behind it. The rest is just trying to pack everything in as short as possible, in a proof that is as short as possible. So now, why can we generalize this to something like relax R1CS, where our statement is something like that, right? Like we have a scalar, we have a public input, and we have the commitment to the error terms and the commitment to this witness. So the idea is that actually now what we need to prove is a different Hadamard relation. So we are trying to prove that there are some vectors A, B, such that U times C plus some error terms are holds, right? So, but since this like Hadamard relation is like sort of universal, actually, we can actually prove that without really changing the SRS. We just have to change how we verify stuff. On the other hand, for the linear relations, we are trying to prove something like this, but we also need to prove that this commitment that we are given as input, so the W, really matches the same Z that is used for A, B, and C. So here, we really need to change the structure reference string, okay? Because we are proving a new linear relations, and as I told you, these linear relations are not universal. So you need to adapt the SRS to prove these kind of things. This is similar to changes you need to make if you want to make your SNARK commit and prove, because at the end, this is essentially what you're doing, okay? Now you want to prove that ABC satisfy this, and that you have a commitment to this Z, no? That this, so you're giving this as an input, so you're giving a committed witness, and you have to prove that this committed witness is also the one you're using for the relations. Okay, so essentially that's it. So we add, like you could design your SNARK by adding some trapdoor to prove one extra linear relation, and then the Hadamard relations, like sort of you get this for free. Unfortunately, there are additional complications because because this, like the statement E and W is created by the prover, so it can be adversarial, right? So it doesn't need to be correctly computed commitments to the error terms. So there are like additional trapdoors that I need to put in the SRS, that we need to put in the SRS, so that we can also make sure that they are more or less correctly computed, okay? The final result is we get something like that. So we have the SRS includes the commitment keys that I'm using for committing to E and W. It adds this extra term, which is essentially proving this extra linear relation that I need for making the scheme commit and prove. And there are these other trapdoors and these commitment keys that are thought. The role they play is to make sure that E and W are extractable and are correctly computed. Okay, the verification equation that you get is this. So you can check that the proof size is the same, but of course now you have that it includes the statement. So there are 2 extra group elements that you don't have in group 16, okay, because your statement just has 2 group elements. And you also need to do 2 extra pairings. There is an exponentiation in the target group, but in fact, well, this is a bit of a static reason. Like if you divide everything by U, then you don't have this exponentiation in the target group. And that's it. So that's the end of the talk. Thanks. I don't know if there are more questions.
So first of all, thank you very much for the presentation. I think it was crystal clear, so it's appreciated when this happens. I have one question related to the relaxed R1CS prover, and it's: do you foresee any improvements that could happen? Like when you wrote the paper, did you find any ideas, as we discussed previously with FLIP, that you were like, okay, this is something that has potential and we could continue looking forward?
So as I said, like what I want to look for now is like folding different instances. For relaxed R1CS, so for the last step, I find it, so I think you can probably reduce communication complexity by using techniques like that have been recently, so there's this paper of Lipma, Polymath, and there's this, I think there's this recent paper also, probably it's Pari or Garuda, but from this new paper. As far as I understand, these papers are using have shorter communication complexity, but the price that they pay is that you're arithmetizing differently, right? I think you're moving to some kind of square span program or something. And so in this sense, like I think you could reduce communication size for Relax R1CS as well. The question is if this trade-off is interesting to you. I have difficulty seeing what can you do better with this growth 16. Although, as I said, like when you design such a SNARK, there's not a single trade-off possible, right? Like in fact, this took us some time because we had like different possible ways of building it. Like, do we want to put a random oracle, but maybe then you change the setup in less, right? Like we were concerned about changing the setup because we know that from an engineering point of view, it's complicated.
Yeah.
We know that I think you cannot avoid it related to this. In a certain sense, you cannot avoid it. So you cannot avoid somehow to have this, extra term to prove this extra relation because it's related to make it commit and prove. The question is how many extra trapdoors and how special do you want your commitment key to be? I forgot to mention that we analyzed when we did the security proof of this SNARK, we also analyzed it in a model that takes into account the powers of tau ceremony that you would run to generate the setup. So I don't know, like for growth 16, right? As you know, there was this paper of powers of tau. Where they showed that actually growth 16 is still sound if you publish some intermediate values, right? Like this this U's times betas, this V times alpha, and so on, right? So we did the same analysis. So our security proof is like in this stronger model where we show that these intermediate values that you would need to run the summary wouldn't affect soundness. But of course, like we understand that this is like in practice and it can be an issue.
That makes sense. Mainly asking that because of the fact that, as you correctly say, if you need to constantly, let's say, modify the SRS, it's not just the challenge of you need to hold a lot of memory in your device to be able to keep modifying it, but also the fact that once you want to run the decider amongst all of this communication, you need to redistribute new verifying keys to whoever wants to verify this computation because the SRS was just changed. Is that correct, or am I like just missing something, which could definitely be?
I don't know if we're understanding each other completely because this does not depend on the Relax R1CS instance. Is this so when well, I'm not sure okay, so this is the same key once you fix ABC, yes?
I see. Okay.
It's not like a key for E.
Okay. I was still in the setup of, since we are proving commitments of commitments, we can just go with whatever. But yeah, you're completely right. That makes sense. Okay. I think there's a question in the chat from Pierre also. Thanks, this is really cool. Is there any reference implementation?
No, we don't have any implementation. No, we don't. we are not we don't have the capacity, any of us three, but we would be happy to talk if somebody is interested.
Cool. Okay, good to know. Yep, I agree. Is there any other questions from anyone? I'll take it as a no. So once again, thank you very much, Carla, for doing this presentation. It was really nice, to be honest. I really liked it. And thank you everyone for attending and spending the time here. I'll see you around.
Thank you, Carlos. Goodbye.
Cheers. Bye-bye.
Thank you, everyone. Bye.